Hello friends, welcome back to my YouTube channel. Today I'll discuss the steps involved in the McCabe Thiele method. So this is a part of my discussion on distillation. It is 29th part, and today we will know what are the steps involved in finding the number of stages in a typical trade column. We will learn how to find a number of stages using McCabe Thiele method. So let us start this session. What you understand today? So now you will learn how to use the McCabe Thiele method for the finding a number of stages in a typical trade column. So at the end of this discussion, you'll be able to find the number of stages in a typical trade column by using McCabe Thiele method. Actually, the McCabe Thiele method, it gives the number of ideal stages. I will know more about it. It gives the number of ideal stages that are needed to bring about the desired separation by fractionation. And what is fractionation? Fractionation is multi-stage distillation that is carried out in cylindrical tray columns. Distillation is carried out in typical tray columns. Okay. Now let us understand what is a stage before knowing what is an ideal stage, because the McCabe Thiele method is going to give the number of ideal stages. So let us first understand a stage. So a stage, it could be a device or a combination of devices in which two insoluble phases, they come in intimate contact with each other. Mass transfer occurs between them, tending to bring them to equilibrium. And after they are at equilibrium, the two phases are then physically separated from each other. So a device in which all these three things happen, that is, two insoluble phases, they come in intimate contact of each other. Mass transfer occurs between them, tending to bring them to equilibrium. And finally, the two phases are physically separated from each other. So a device, or it could be a combination of devices in which all this happens, is called a stage. Are you understanding it? So a stage is a device or a combination of devices in which two insoluble phases, they come in intimate contact of each other. Mass transfer occurs between them, tending to bring them to equilibrium. And finally, they are physically separated from each other. So that constitutes a stage. Okay. Now, let us understand what is an ideal stage. An ideal stage is also called an equilibrium stage or theoretical stage. Okay, so an ideal stage or an equilibrium stage or a theoretical stage. What is it? Let us understand. The stage in which the insoluble phases leaving the stage, they are in complete equilibrium with each other. When complete equilibrium is achieved before the two insoluble phases leave the stage, then that stage is an ideal stage or an equilibrium stage or a theoretical stage. Okay, are you understanding it? So a stage in which insoluble phases, the two insoluble phases that leave the stage, they are in complete equilibrium with each other. Okay, so when you are talking about distillation in trade column, or simply in the case of trade columns, each tray in that column, it acts like a stage. So on each tray, two insoluble phases. What are the phases involved in this case? The phases involved are liquid and vapor phases. So you have two insoluble phases and that are liquid and vapor. Okay, so if you have to understand it with the help of this diagram, so I'm showing a single tray over here. Now in the tray column, this tray is going to act as a stage. So what happens? Two insoluble phases, they come to that tray. There is intimate contact between them. In this case, liquid is coming onto the tray, vapor is also coming onto the tray. There is an intimate contact between them. Mass transfer occurs between them. They try to go to equilibrium and then they leave the tray or the stage. Okay, so the tray in this case is acting as a stage. Okay, so when the leading liquid and vapor phases, this is the leading vapor phase, this is the leading liquid phase. So when the leading liquid and vapor phases are in complete equilibrium with each other, then this tray will act as an ideal stage or an equilibrium stage or a theoretical stage. Okay, so the concept of an ideal stage is when the leading phases, that is vapor and liquid phases in this case, they are in complete equilibrium with each other. So such a stage is an ideal stage. So you're understanding it. So first we have understood what is a stage, and then now we have understood what is an equilibrium or an ideal stage. Okay. In reality, an ideal stage is hypothetical or imaginary. Meaning is it does not exist in reality. It does not exist in reality. In reality, what do you have? You have the real stage. And what is a real stage? The stage in which the insoluble phases are leaving the stage. They are not in complete equilibrium with each other. Sorry. A complete equilibrium is not achieved. And real stage is not able to bring complete equilibrium between the leading phases. So again, you can understand this with the help of a schematic diagram. So you have a liquid phase coming in contact with vapor phase on the tray, which is acting as a stage. There is an intimate contact, mass transfer occurs between them, and then they leave that tray. So when the leading liquid and vapor phases, they are not in complete equilibrium with each other, then that stage will be acting as a real stage. In reality, every tray in a typical tray column is a real stage. What do you mean by real tray or real stage? The leading phases, in this case, vapor and liquid, they are not in complete equilibrium with each other. Okay. Then the next thing that we are going to know is the efficiency of a real stage. So since real stage is not able to achieve complete equilibrium, it will try to go close to equilibrium. And how close it goes to the equilibrium is described in terms of its efficiency. So the efficiency of a real tray, it actually demonstrates its ability to establish an equilibrium between the leading states. How well an equilibrium is established between the leading states, it tells you about the efficiency of a real state. Okay, so again, let us understand with the help of this diagram. So you have the two leading phases, vapor and liquid. First thing that we should know, a complete equilibrium is not possible. A complete equilibrium is not possible with a real tray. But in this case, closer to a complete equilibrium, more is the efficiency. So as you go closer to the complete equilibrium, more efficiency is possible in the case of a real stage. Okay. So for tray columns, we have what is called the overall tray efficiency. And how it is defined? It is defined as Ni upon NR into 100. What is Ni in this case? Ni is the number of ideal stages. In tray columns, these are trays. And NR is the number of real trays or stages. And we should remember that number of real stages, that is NR, is always greater than number of ideal stages, that is Ni. And therefore, as per this equation, efficiency will always be 100%, less than 100%. For ideal stage, it will be 100. It can be 100%. It is 100%. So for a real case, efficiency will be less than 100%. So this equation, Ni upon NR into 100, is giving us the percentage efficiency. So it is actually percentage efficiency. Percentage efficiency is equal to Ni upon NR into 100. Okay. And McCabe Thiele method is going to give us Ni, the number of ideal stages in the tray column. And now we know in a typical tray column, each tray is acting as a stage. Okay, so here we have understood what we mean by the efficiency of a stage, and then in the case of tray columns, how to describe its overall tray efficiency. Okay, so once you know the number of ideal stages, like once you know the efficiency, you can find the number of real stages in a typical tray column. Okay, so having understood the basic concept, let us now go to the steps in the McCabe Thiele. So what is known to us when you have a problem to solve? What is known to us? What information is given to us that can be used to find the number of stages in a different tray column? Let us understand. First thing is, you know the feed. And in our case, it will be a binary liquid solution of two components, component A and component B. Okay. So A in this case is the more volatile component. That is, A is having a lower boiling point and higher liquid pressure. So F and XF are known to us. What is F? F is the molar flow rate of the feed solution. So it is, for example, it could be kilomole per second molar flow rate. And what is XF? XF is the mole fraction of A in the feed solution. And what is A? A is the more volatile. Then XD or XW or both are known to us. What is XD? Mole fraction of A in the distillate. And what is XW? Mole fraction of A in the bottom products. So either XD is known to us or simply is known to us, or both of them are known to us. And then you have D or W, or both will be known. So D is the molar flow rate of the distillate, and W is the molar flow rate of the bottom. Okay, so if both say XW and XD are known to us, if both XW and XD are known to us, then W and D, they will not be known. We will have to calculate W and D side this time. W and D, they will not be known to us, and we will have to calculate by taking out that. Then the reflux ratio is known to us. That is the ratio of the reflux that is coming into the column at the top divided by the distillate flow rate, distillate molar flow rate, molar flow rate of the reflux divided by molar flow rate of the distillate. This is known to us. Reflux ratio is known. The VLE data, either the VLE data will be given to us or the relative volatility will be given. So in that case, we will have to use the value of relative volatility to find or to generate the VLE data. I'll tell you how to do it. And I hope you know what is VLE data. So I have discussed about it in my earlier videos. I will give link to the relevant videos in the description section. Please go and watch those videos. Okay? And finally, what else is known to us? Weight on the type of the feed. Weight on the type of the feed. Type of the feed is known to us. So feed could be one of the 5 types that I have discussed in my previous videos. Okay, so with this information I will repeat. Let us learn how to find the number of stages in a typical trade column. Okay, step number 1. So I'm discussing it as steps. So let us first understand what is step number 1. So some quantities may be unknown. So step number 1 will be finding those unknown quantities. So which are these quantities? So which quantities are involved? You have the feed flow rate, molar flow rate, F, mole fraction of E in the feed, XM, molar flow rate of distillate, mole fraction of E in the distillate, molar flow rate of the bottom product, and mole fraction of E in the bottom product. So these are the quantities involved. Now, in any quantity, any quantity out of this may not be known to us. So our first task would be to find that quantity by quantities. So any unknown quantity from the above list, it has to be calculated or it has to be found out. And how are you going to how are you going to calculate that? For that, you are going to use steady state total material balance and steady state material balance for A, which is the more volatile compound. So you have 2 equations that can be used to find any unknown quantity. Okay. So the equations to be used in this case is you have the steady state total material balance, F is equal to D plus W, and steady state material balance for the more volatile component, which is F into XF, that is equal to D into XT plus W into XW. So you have 2 equations, and these 2 equations can be solved simultaneously for finding any 2 unknown quantities. Here, so these equations, they can be solved simultaneously, and by doing that, you'll be able to find any 2 unknown quantities out of this 6. Okay, so first task would be to find out any unknown quantity in this way. Okay, I have discussed about this balances in my earlier videos on distillation. Okay, then let us know step number 2. That ends step number 1, where we have found out any unknown quantity. Then you have step number 2, in which you are going to plot the equilibrium diagram, plotting of the equilibrium diagram, which is also called the distribution diagram, or which is also called the XY. So for that, first possibility is the VLE data may be given to you. So if that is the case, then you can directly plot it. So VLE data is nothing but X and Y values that are directly with each other. Mole fraction of E, that is mole fraction of the more volatile component in the liquid phase, and then mole fraction of the more volatile component in the backward phase. Okay, so will be provided with values of x and the corresponding values of y. Now in this case, your job will be to simply plot this two values against each other. So you'll be plotting x on x-axis and y on y-axis. And this is the diagonal line which I have drawn for reference, or which is to be drawn for reference. And the plot will give you this curve, and this curve is nothing but the equilibrium curve or the distribution curve. Okay? So in this way, in step number 2, if the theory data is provided to us, we are plotting the distribution diagram or equilibrium diagram or the XY plot in this way. Now, the case may be theory data may not be provided. Instead of that, then they give us the value of relative volatility, alpha AB. Volatility of A relative to B, it will be P1 to A. So in that case, we need to generate the theory data. And how are you going to generate the theory data? For that, you can use this equation. Y is equal to alpha ABX divided by 1 plus alpha AB minus 1 into X. So what is the approach? The approach is to assign some values for X. So for example, this could be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. And for each of this value of X, we are going to calculate the corresponding value, or we have to calculate the corresponding value of Y. And then you can report those values in this table. And once you have all X and Y values, you can plot them against each other to get the distribution. Okay. So if equilibrium data, that is really data, is provided to you, so you can directly plot the data. If instead of really data, alpha is given to you, that is relative volatility is given to you, then you can use this equation to first generate the data and then plot the distribution type. Okay, now let us move ahead. Now let us know what will be done in step number 3. In step number 3, we are going to plot the rectifying section line. And for my, I have discussed about rectifying section line in details in my earlier videos. You please watch those videos. So for plotting the rectifying section line, what information is available or what information has to be used? Let me take it. First, in rectifying section line, it intersects with the diagonal line at a point which has coordinates of xd, xt. So we are going to use this information. And then the other information is it is making an intercept on the y-axis. And what is that intercept? Intercept is xd upon r plus 1. So these two informations we are going to use to plot the rectifying section line. Okay, so I showed you the distribution diagram. So we have plotted x on the x-axis, y on the y-axis, and we have drawn the diagonal line, and you get the equilibrium curve. Now let us know how to plot the rectifying section line. So for that, I'll be first locating this point, xd, xt. Xd is mole fraction of the more volatile component in the distillate. So it will be a higher value. So for example, it could be located over here. Okay. So from this is xd. I go to the diagonal line. And if I go to the y-axis, this will also be equal to xt. So first thing is the operating line for the rectifying section when we're starting at this point. Then I will locate the intercept. Intercept is xd upon r plus 1. So knowing all since all the values will be known to me, I can get this value. So that intercept will be located somewhere here. This is xd upon r plus 1. So I have 2 points. And now I know the rectifying section line passes through this 2 points. So simply I will draw the rectifying section line. Okay. So in this way, the rectifying section line is drawn. So for this, we have used this information. You can intersect with the diagonal line at xd, and it has an intersect of xd upon r plus 1 on the y-axis. Okay, so that ends step number 3. Now, step number 4 is plotting of the Q line or the feed line. And how it is done? For that, we are going to use the following information. What is that? First is it intersects the diagonal line at a point which has coordinates of xf, xf. Okay, then the slope of the line, slope of the feed line also, slope of the Q line is Q upon Q minus 1. And Q, it depends on the type of the feed. So I have discussed about this in my earlier videos. I'm giving links to those videos. You please watch those videos. So Q, the parameter Q, it depends on the type of the feed. For example, for our understanding, let us consider the feed to be a partially vaporized feed. And for a partially vaporized feed, the slope of the Q line is negative. How it is negative? Again, please watch the video. Okay, so for we are going to consider a partially vaporized feed in order to understand the concept. Okay, so how to plot the Q line? So you have this distribution diagram where we have plotted in the previous step, we have plotted the rectifying section line. Now, let us plot the Q line. For that, first we will locate the point with coordinates xf, xf. So xf may be more here. With this xf, I go to the diagonal line. And if I go to the y-axis, this will also be equal to xf. The Q line will be starting at this point, and it will be placed according to its slope. And we have considered a partially vaporized feed, in which case slope of the Q line is negative. So for example, the Q line could be like this. Okay, so in this step, we have learned how to plot the Q line. Okay, let us move ahead. If you have any doubts in the discussion, you please mention those in the comment section. Okay. So after step number 4, you have step number 5, where I will be plotting the stepping section line. So what information is available for doing that? First thing is it intersects the diagonal line at a point which has coordinates of xw, xw. And the second information is the stepping section line is going to pass through the intersection point of the rectifying section line and the Q line. Okay, so two points on the line are known, and you can see it on the stepping section. Okay, so with this, let us know how to do it. So in step number 4, we had got this, we were at this stage. We had plotted the Q line in the previous step. Now our job is to plot the stepping section line. The first information is it passes through a point which has coordinates of xw. So I locate that point. So here it is xw. xw will have an overvalue. So I go to the diagonal line. Then on x-axis, it will also be xw. Stepping section line will start at this point, and then it is going to pass through the intersection point of the rectifying section line and the Q line. So this will be the stepping section line. Okay. So in this way, you have to plot the stepping section line. Again, you must have noted the 3 lines, like a rectifying section line, stepping section line, and the Q line. They intersect each other at a single point. Okay, so with this basic structure now formed, we are going to use this to find the number of stages. Okay, so now let us know how to find the number of stages. So this will be done in step number 6. So I just show all the steps. So first step is plotting up the distribution diagram, where X is plotted on the X-axis, Y is plotted on the Y-axis, and the diagonal line is drawn for the reference, and then you have the resulting curve. That is the distribution diagram. First step is you'll be locating, or you'll be drawing the rectifying section line. So you'll locate XD, you'll go to the diagonal line, then to Y-axis, it will be XD. The rectifying section line is going to start at this point. Then you locate the intersect, XD upon R plus 1. You have this point on the Y-axis, and the rectifying section line is going to pass through these 2 points. Then the next step is to draw the Q line. So for that, XZ will be located. The point XZ will be located on the diagonal line. Q line will be starting at this point. So its placement will be according to its slope. For our discussion, we have considered it to be partially vaporized speed. So for that, Q line will be looking like this. Then next step is to locate or to draw the stripping section line. It starts at a point which has coordinates of XW, and then it passes through the intersection point of rectifying section line and Q line. So this will be the stripping section line. So once the basic structure is ready, now we are ready to plot the stages. So you start at this point, and the point where rectifying section line intersects the diagonal line. Draw a horizontal line till you reach the equilibrium curve. Once you reach the equilibrium curve, you draw the vertical line till you reach the rectifying section line. Then continue this. Then I will be drawing a horizontal line to reach the equilibrium curve, and then a vertical line to reach the rectifying section line. Then again horizontal line to reach the equilibrium curve. Now in this case, what has happened? When I had drawn this horizontal line, I have crossed the intersection of the 3 lines. The intersection point of rectifying section line, Q line, and the stripping section line. So once I do that, when I draw a vertical line, this time I have to go up to the stripping section line. Okay, then again the procedure will be continuing. I'll be going to the equilibrium curve and then to the stripping section line. And when I draw the horizontal line next time, what is going to happen, or what is happening? The point XW is getting crossed. Once this happens, your procedure stops. Okay, so the next vertical line will be simply drawn in this way. This will be the last stage. Okay, so 2 things are important. You are constructing these triangles by drawing horizontal lines. So you are going from, so you are starting with XD, going to the equilibrium curve, then to the rectifying section line to the equilibrium curve, rectifying section line, equilibrium curve. And once you cross the intersection point, now you have to move to the stripping section line, then to equilibrium curve, to the stripping section line. And once you cross the point XW, you have to stop. Okay, so this triangles will be, each of the triangle will be acting, will be an ideal stage in this case. So this is ideal stage number 1, ideal stage number 2, ideal stage number 3, ideal stage number 4, and ideal stage number 5. Now actually, this step number 5 in this case is the reboiler. That's why I'm denoting it as R. So R is that stage which has this point in it, XW, XW point in it. So that will be the reboil. Another important thing is just look at the stage where the 3 lines intersect with each other, because that will be the feed gate. Feed stage, you can say. So above the feed plate, you have stages in the rectifying section, and below the feed plate, you have stages in the steeping section. Okay? So in this case, the number of ideal stages, that is Ni, is equal to 4 and plus 1. And what is that 1? That is nothing but the reboiler. So it is the triangle in which you have the point XW. And if somebody asks you to tell what is the number of feed plate, then you can tell. In this case, it is 3. Why it is 3? Because in the 3 lines are intersecting on this stage. Okay? So in this way, you can find the number of stages in a typical tray column by using McCabe Thiele. Remember, McCabe Thiele method is going to be the number of ideal stages, and then knowing the efficiency, overall tray efficiency of the column, you can find the number of real stages. So with this, I end my discussion for today's topic. I hope you have understood the concepts. I hope you have learned how to find number of ideal stages by using the McCabe Thiele. In my next video, I'll be discussing a numerical where we will be using this method to find the number of ideal stages. Thank you for watching my video. Do subscribe to my YouTube channel. Tell your friends to subscribe to it. And also hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Okay, thank you.